And now let's start with some basic geometry processing functions to have a walkthrough. Our code is presented with Jupyter Notebook, and all code are going to be available also in the binary instance. The installation process for the basic libraries we're going to use is libgl, meshplot, and numpy. They're all accessible in the channel of Conda Forge. And once you have everything installed, you can import them. And let's start from the basics. So we have a two matrices, and one is called V, that's going to be the vertices with 4 rows. Each row will have three numbers representing the x, y, and z coordinates. And we have another matrix of F that's having 2 rows. Each row has 3 elements, meaning that it's a triangle forming from the 0th, 1st, and 2nd points. And the second triangle is the 1st, 3rd, and 2nd points. So if we plot this out, we will get 2 triangles. And we can drag to rotate it around, get a better sense of it. And eventually we want more triangles. This can fortunately be done with our libgl functions. And we can read a lot of formats, the most generic one being read triangle meshes. And here we're going to have a docstring. The input argument is going to be a string. And here in our folder, we have bunny.off. And the return value are 2 matrices, V and F, which is what we had just been seeing. And then we can plot this V and F. And we can see we have a bunny. We want to do something more with this bunny. And what we can do here, we can assign some color. Let's come up with a simple vector field on this surface. So our V is a matrix of 3,500 by 3, and our F is 7,000 by 3. We'll just slice. This gives us the first column of V, and we can use it as a color map. So we plot V and F, we give it additional key C, that means color, and we're getting a model with colors. There are a lot of other things you can do easily with this Python interface. For example, we want to show maybe only partially of this mesh, half of the bunny, to see some a slicing effect. So let's say we want to only visualize the triangles on the left. So we need to first try to identify them. This can be done through, let's compute the barycenter of each of them. And let's see what we get. The shape is about 7,000. It's the same shape as your F matrix. So again, you can take the first column. This is going to be a vector, and you see there are negative values. So let's make it larger than 0. And we can directly using this to slice. Okay, we get this butt of the bunny. Maybe the head is more interesting, so we put smaller than 0. And now what you can see is this bunny. Let's maybe change the slicing function. So here is x smaller than 0. Let's try x plus y smaller than 0. We only get the feet. So we can make this range a little bigger by 0.1. And now what we can see is this most of the bunny, this half of the bunny is here. And through this hole, we can observe the triangles below. And honestly, there are like a few bad triangles. But that's not of our concern today. So we proceed to some other visualizations. So our mesh plot library also supports some more advanced visualization, for example, vector field. If you think about it, vector field is just some quiver lines on this shape. So we have we start with a shape plot, and then we want a vector field. The simplest of all is the normal field. So per face normal, okay, how do we do it? We have a V, an F, and for a fallback for degeneracy, and we just put a trivial one here. Okay, so this is a matrix again, the same shape as F. And what are we gonna do? First, we're gonna get V and F, and now we want to add some lines, add some quiver lines on top of this. So we add P. We have a function called add lines. Add lines accept two parameters, start and end. The start is, we have the barycenters we had before, and the end is BC plus NF. Wow, this is a ball. What's happening? We see there's, let's zoom in. Okay, there is a bunny inside, but the lines are just too long. This is because our bunny is smaller than the unit cube, but the lines here are unit length, so it's not the same scale. If we put 0.1, it's looking better, but we should put it 0.01. This is the correct scale, and we finally get a picture. Apart from this normal field, there are other interesting fields. For example, principal curvature is a common thing we use, and it estimates the shape. Again, it takes the necessary arguments of V and F, and it returns four matrices. PD, let's write this down. PD1, PD2, PV1, and PV2. So PD are the curvature direction and the principal curvature direction, and PV are principal curvature value. They live on vertices. Okay, so we get back here. Now we don't use normals, but we use this new lines, PD1 V plus PD1. Still, let's do a scaling. Maybe we can make it a little bit shorter. Yeah, this more looks on top of the surface. And we add the other set of lines, V plus 5E minus 3 times PD2. And we can see immediately see a vector field showing it up itself. And we can add the line color to be red. For the second plot, we do the same. Line color blue. So I have a red blue visualization. If you think this is a bit boring, we can also give some colors. So C equal to, since we already added, so we can do a average of the two principal curvature values. If you are familiar with differential geometry, you know this is the mean curvature. So we have a shape that captures differential quantities in a nutshell. A good thing about this is that you can now share with your possibly share with your colleagues. Here, our variable p encapsulates a mesh plot viewer, and we can do p.save test1.html. Now it saves the file to HTML, and if you open it from the terminal, you will get a model, and you can share this HTML file with your colleagues, and they will your work on. The next section, we're talking about mesh statistics. So we still have this bunny that we're working with, and let's start by using some existing LibIGL functions to check. For example, we can check if it's manifold. Yeah, here is a function called isEdgeManifold. Okay, it's manifold. That means good. And we can find irregular vertices. And in here, it simply means whether this it have 6 neighbors or not. And this is just a list of Boolean values. And presumably, we can do count and 0. And we will know that like 60% is irregular vertices shape. The same thing happens with double area. We have a double area, and we have just a vector that's the same shape as the number of triangles. It's many numbers, and sometimes we want to make sense of it. One thing we can do here is that we can use a lot of existing libraries from Python. One library I particularly like is Plotly. Import Plotly graph objects. And let's construct a figure. Histogram x equal to double area. And we get a histogram now. You can do other fancy plots like violin plot to get more sense of it. Some other useful statistics, you can do internal angle. This is giving a matrix the same shape as your F matrix. So it means for every triangle, you have 3 angles. Every triangle has 3 angles, and it's recording them all. If we want to get some statistics, we may want to we may want to flatten this. So it's unrolled, and the violin plot And let's switch back to histogram plot. These numbers are a bit difficult to interpret because it's in radian. We can just convert it to on the spot to degree, and we can see the majority is like 50 degrees, so that's a good sign. And but there are a few bad elements. There's 172 degrees, and also on the other hand, there are like very small degrees between 3 and 4. So this mesh may need some improvement if you want to use it. And also we can directly see what is, for example, the minimum. This is this is probably a difficult thing to interpolate because it's going to give you the unrolled indices. But what we have is this phase. Let's see whether we're yeah, this phase has a small angle, and maybe we can just see it. Let's start with this, and for small triangles, it's quite useful to visualize by points. Okay, so as we were expecting, it's actually on the bottom. So we can enable the wireframe and point size, and yeah, we need to do it when we're plotting the mesh. This is not really clear, so we make the point size a bit smaller. But we roughly get an idea what this problem with the triangle, where the problem is. Enough with the bunny. For the next step, we're moving on to the new application, the next application of texture mapping. So again, we read this topology mesh so that it's easier to deal with. Read the triangle mesh. This is a nice model of camel head. We're using harmonic parametrization now, so that means we're mapping this shape into an actual disk with harmonic weights. And the first thing we're gonna do is to try to identify where is the boundary loop. This gives us a list of indices, and then we just plot this, and probably we can add points. And yeah, as we're coding, we are able to visualize the result interactively. We can see that we are setting correctly all the boundaries here. So then the next thing we're going to do is we're going to assign this. This is just a helper function to assign the vertices to the uniform to a uniform sampling on a sphere. Okay, we can we can actually see what is this boundary UV giving us, and it looks correct. Then we just calling igl.harmonic weights. This is again a big function, so we just follow the documentation VF and its boundary UV and k equal to 1, and it returns the UV. Okay, let's see what this UV is. It's a, as expected, it's a matrix, and if we look at the point cloud, is this shape. And if you're familiar with parameterization, you know you can assign it with a face. And let's enable the wireframe. So an interesting thing you may notice is that this is not looking like the camel head before, but in some sense there are eyes and ears showing up. This is the kind of conforming property of the harmonic map. And here we can give it another parameter called UV. What this parameter do is that it will tell the model where is the UV map. And here, because the mesh is the same as UV map, you just get standard checkerboard. But if you can plot this on the original head, you will see, okay, this is how the mapping works. One thing in particular I want to mention is that we have another parameter called texture data that controls where you can change to get a different checkerboard. And we have function called gen checkers. If we do 50-50, it's going to get a denser checkerboard. Now we store it in a checker. It's a bunch of floats, and it's 256 by 3. And 3 means the RGB channel. If we put checker here, it's still giving you the same result, but you just get the denser checkerboard, so you see clearly what is wrong in terms of distortion. And for different model, you may want to use different parameters. For example, if you do 100, you get probably too dense around the neck, but it's good for you to do some manual inspection. This checker is not nothing special. It's just a 2D image. So it's just a height 256 with 256 by 3 RGB channels. So you can give it a new image and put it into texture data, so you can have your customized texture checkers. For example, if we import matplot lib.py plot, we can import the common function of image show, and then image show it's just probably we can look at a bit coarser, and this is just a checkerboard image of a checkerboard. So if you give it another image, it will have some different checkerboards and to satisfy your aesthetic concerns. And if we come back to our original camel, we have this problem of excessive distortion. There are actually a number of strategies implemented in libIGL. We're going to use one of the other ones. as rigid as possible surface parameterization. So we have V. We look at, this is not as good documented, but we have VF and dimension. VF dimension is 2, and we need a required argument of B. B in Lebesgue usually means the boundary, and we're giving it something empty, and it saved this struct to a variable called arap, and it can the first line does some pre-computation, and second line does a soft iteration, and we still need the boundary condition and the initialization UV from the last iteration. So we get a better UV. Let's see how it works on the. And we use the same texture data as before, so that it's more. So as you can see, we get same number of black squares, but in this case, it has a bit more angular stretch, but area-wise, it's better. And here we get much better result in terms of the distortion. The next thing I want to show is another classical geometry processing task that can be made easy when you prototype. Let's do a simple Laplacian smoothing. Following the tutorial, we use this model for Cal. So you can just read it and visualize it so that you know you're reading the right thing. This is the model we want to use, and now that we have a model, let's see what we want to do. Convert to a markdown block, and let's write some math. So the formula I'm gonna use is you start from a V, a vertex coordinates, and you want to add some lambda of Laplacian. This is the original formulation that so what you want. So what you want to have here is the difference between two iterations is being the Laplacian of this shape. And we do backward Euler, we do backward Euler such that we can just set 1 here. Okay, and there's a negative sign, so we're actually doing we're putting this onto the left and this onto the right. We are this L here is actually the not the weighted Laplacian that's not symmetric. So we're going to multiply everything by a mass matrix such that the system we're solving is symmetric, and also we group this together. To have a m plus plus lambda, this cotangent lambda, cotangent Laplacian, and this is on the right. Okay, so we read this. We read this v. This is going to be the initial v, and we have cotangent matrix. For some reason, this is negative. We need to. The cotangent matrix actually gives the negative. And then we have a mass matrix that's VF. So our new coordinates is it's a system solve of m plus small scalar times L, and the right hand side is m product with B. Let's see what this gives us. For this solve, we're gonna use this SciPy function. Dot linear algebra import. It's called sparse solve as solve. We're just giving it a new name, and let's see what we get. So here we actually get a cow that's slightly smoothed out, and this is indeed what we're expecting. Now we want to repeat this process multiple times, and maybe we can store this into a list. For in range 10 means we repeat 10 times. One trick we're gonna use is we're gonna only recompute m every time, and we can just write onto this V matrix. So this briefly, for each iteration, we're computing a mass matrix and we're solving for the next iteration, and this goes on and on for 10 times. And one thing I want to show here is that we can add some UI to this process. Let's have a function that's showing the initial V and F. And we can have a function called mean curvature flow. Let's get an argument level. And for each level, what we're gonna do is we're gonna update the object and update versus such that it becomes this particular level in this matrix is serialized. And we're going to decorate this with Jupyter widgets and give it range from 0 to 10. So now this is input, but as you slide this, it becomes an ellipsoid. If it goes enough iterations, it will become a circular. And you can slide this before and after just to have a relaxing moment. There are a lot of other functions in libIGL that you can actually play with in Python. You can refer to the tutorial for more examples, but for another example, I'm gonna just have some fun and get a good picture out of it. Let's just read a mesh. Let's read the bunny mesh again. And just see if we get the right one. Okay. Okay, this looks good. I want to have some plot this bunny with some stripe patterns. And I'm gonna use geodesic to do it. So I'm looking at the documentation of exact geodesic. We need to have an input function called VF and VS, VT, and the others are not required. And what is VS? VS is a source vertex. So here, let's just pick the first one. And target everything. And the output is a vector of D, and the shape of D is supposed to be the shape of VT, which in turn the shape of E. So this actually gives us a scalar field on the surface, and we can visualize it this way. And it's quite clear that this source is somewhere here, but we can make this clear by just directly we can make it smaller. Okay, it's clear that it starts from this way, and it's giving you this scalar field. And we can apply some periodic function. The simplest one is sine function, with the hope that we apply something periodic and it will have some wavy pattern. But this is not doing the right thing. And what is the problem? So let's look at D. It seems that D is too small. So we get some just simple descriptions. This is from 0 to 0.15. It's too small to be covered by the sign, so we do 100. And we can make this a bit more sharp by additional doing an absolute value. And now we have a bunny with this stripe patterns. Let's look at, and we can also try to reduce the effect of shading by setting to be not flat. This is not looking so great because there are some leaking colors. This is because of insufficient resolution. What we can do here is, let's just go back and do some loop subdivision. Okay, run this again. This takes a little bit more time, but worth it. We can now have a visualization of this bunny with this cute sweaters, cute stripes. There are other options, for example, the ByGL ISO lines that actually do this better, but this is a very simple demonstration. I'll achieve it. And this concludes the first part of our playing around.